Alrighty, let's begin. Hi everyone, welcome to the next episode. So this would be the phase 2 of our LLM series, where we would move towards more contextual and more meaning kind of a word representation, right? And in this episode, we'll understand more about the word embeddings. So initially in the bag of words, the problem was the queen, the king, they were both treated as very different sort of an entities, very different sort of words, right? And if you try to find the difference between a king and queen or a king and apple, the model will not be able to differentiate between these words, right? Because it is only looking at frequency of occurrence of those words in the sentences or the corpus, right? So that's the reason why the bag of words were not able to get the essence or the meaning of the words and the relations between the words, right? Similarly, we also talked about TF-IDF. Now, TF-IDF, suppose I have an example where I have laptop and desktop, right? Now, TF-IDF will not be able to understand that these both are actually something which are very similar. A laptop and desktop are basically used for the same functionality, are quite similar, but the TF-IDF will not be able to segregate that or get the essence of it. So that's where things like embeddings come into play. Now, of course, we would go into each of two or three embeddings in details, but for now, for getting the essence of what embedding is, so it's basically it projects your words into a high dimension vector. So for example, 300 dimension vector, and then it tries to and then this each dimension tries to basically represent a particular word into a vector space. Now when you look at this vector space, you will find that the vector, the 300 dimension vector or the vector which is there for India would be quite similar to the dimension of India Gate or Delhi, right? Because they are closely related, where Delhi is a city capital of India and the India itself is a country, right? So the positions of these vectors, the word India and the word Delhi, would be quite close to each other, would be quite close to each other, as compared to something like, say, India and then say king or queen, right? So these embeddings helped us in understanding, in getting a more contextual sort of contextual sort of vectors and their representations, basically, right? So I'll give you another example. So in the TF-IDF or word to vec, if I say I love programming and I enjoy coding, these two sentences will not be entirely correlated. But now in the vector space or in the embeddings, what's going to happen is programming would be very close to coding and enjoy would be very close to love, right? Because these are sort of similar words. So this is where you see that embeddings will have a better representation of the words rather than going for just a TF-IDF or any other bag of word kind of a model, right? So that's where these words excel. Now, how are these embeddings basically represented, right? I told you that it's a vector space in a high dimension vector, in 300 dimension vector, or even more dimension of vectors, depending on which model are you using. So after training and learning from the embeddings themselves, this is how you can find the if we project that high dimension space into a 2D sort of a space or a 3D sort of a space, you'll find that the cities vectors are quite close to each other, right? And here you see that the food vectors are quite close to each other. Similarly, body parts, similarly feelings and relatives. So you see, in a very high dimension, your words have been represented in such a way that the things that should come close to each other, you'll find them closer to each other, or clustered with each other, cluttered with each other, right? So that's how you know that the embeddings that you have formed are basically a good embedding, because the things that have to be similar, the essence of similarity is present in these kind of embeddings, right? Now let's look at an example. Now this is a toy data set. Don't consider it that these kind of embeddings are available, but we'll try to get an essence of how exactly the embedding works, right? For example, a cat would be represented in numbers something like that. This, a kitten would be represented something like this, a dog in a house similarly, right? Now what exactly does this particular number means? No one knows exactly how it is finding the relation, but it could be taken as something like the characteristics of a cat, like right? For example, some of the characteristics which it could take is how much a human the cat is, or what is the gender of that particular cat, what is the royalty, how royal the cat would be, right? And you see, based on that, it gives a weightage to that particular characteristics of what makes it a cat, right? Now after learning these characteristics, how it will learn, we'll get to it. But after learning these characteristics, when you reduce your vector space into a two-dimension space, when you project it, do a dimensionality reduction on it, you will find that the similarity metrics, or the words that are similar are actually cluttered or clustered together. So for example, cat and kitten, they are more close to each other in the vector space than something like dog or a house, right? And similarly, there was one more thing which was experimented, and it was seen that the words such as, or the vector representation of something like king, man, queen, women. So if you take the vector of king and you subtract it with the vector of man, and then you add the vector of women to it, you'll find that the vector space is quite similar to, or not exact, but even quite similar to the vector space of the queen. So that's where you see that these kind of relations, these kind of these kind of relations in the vectors gave a trust or a sense that embeddings that are getting formed are basically relevant embeddings, right? Or these kind of embeddings are making sense. It's not just haphazard. So unlike the BoW and the TF-IDF, these embeddings actually captured meanings and relationship between the words. So that's why they were very popular sort of problems, which were very popular ways to represent your words into the vector spaces, right? Now, why exactly was this a breakthrough? Because the words will now have meanings in the numbers, and the AI can compare words based upon the similarities, right? And this was better for the machine learning task as well, where now chatbots and the search engines can basically get a better representation and a better contextual understanding of the words that it is using, right? And similarly, it can also help in machine translations, sentiment analysis, where the AI can understand that happy and joyful are some sort of a similar words, rather than something like happy and car or happy and chair, right? So it helped in a lot of translations and sentimental tasks, sentiment analysis tasks. But how exactly did we train these kind of word vectors, right? So stay tuned for that, and we would be learning a very popular embedding representation, which is known as word to vec, in the next video. So share it with someone who might like this video.